The transistor is, without exaggeration, the most important invention of the 20th century. Without it, there would be no phones, computers, internet, or electric cars. But not all transistors are the same. Today, we will put face to face two champions: the bipolar transistor and the MOSFET transistor, the device that dominates modern electronics. The processor inside your phone contains more than 13 billion transistors. All of them are MOSFETs. Not a single one is a BJT. Why? That's what we will discover in today's lesson. And MOSFETs are not found only in processors. They are present in the inverter of the solar panels on your roof, in your phone charger, and in the control electronics of electric cars. The MOSFET is practically everywhere. I prepared a simple experiment. Two identical circuits, the same load, the same power supply. The only difference is the type of transistor. Let's see what happens. The first circuit uses a bipolar transistor, the 2N2222. We apply a signal to the base through a 1 kΩ resistor. Watch carefully what happens. It works. The LED is on. But look at the multimeter. The base current is about 5 mA. That means our signal source must provide energy to control the transistor. If we look at the power dissipated by the transistor, it is a few milliwatts. That means lost energy, heat that ultimately comes from the battery. Now let's move to the MOSFET circuit. Notice something different. There is no resistor between the control signal and the gate. Why? Because the MOSFET does not draw current at the gate. It is controlled by voltage, not by current. Now let's move to the MOSFET circuit. The LED is on. But look at the gate current on the multimeter. Practically zero. The MOSFET can be controlled almost without consuming energy from the signal source. Let's touch the MOSFET. Cold, almost at room temperature. That's because when fully turned on, a MOSFET behaves like a very small resistance, on the order of milliohms. The energy loss is minimal. Conclusion: the MOSFET is controlled by voltage instead of current and has much lower losses. To understand the difference more deeply, let's use a simple analogy. Imagine two water pipes. On the first one, there is a classic faucet. To open it, you must turn the wheel, and that requires continuous force. If you let go, the faucet closes. That is similar to a BJT. You must continuously push current into the base to keep it open. Now imagine the second pipe has an electric valve. You open it with a button. Just a small electrical signal, no mechanical effort. Once it is open, it stays open without additional effort. That is the MOSFET. Apply a voltage to the gate, the channel opens, and current flows freely from drain to source. Technically speaking, the gate of a MOSFET behaves like a small capacitor. You charge it once with voltage, and then the transistor remains open without consuming additional current. That makes the MOSFET extremely efficient, especially in high-frequency switching circuits. Of course, this analogy is simplified for beginners. Some technical nuances are intentionally omitted. The MOSFET is not alone in its family. Let's briefly look at some of its relatives. Each of them will have its own lesson later. First, the JFET, Junction Field Effect Transistor. Second, the IGBT, Insulated Gate Bipolar Transistor. This is essentially a hybrid device. It is controlled like a MOSFET with an insulated gate, but conducts current like a power BJT. You will find it in industrial inverters, electric locomotives, and welding equipment, applications where voltages and currents are extremely high. Then we have the new generation, silicon carbide MOSFETs, SiC, and gallium nitride transistors, GaN. These devices can operate at higher voltages, higher temperatures, and much higher switching frequencies than traditional silicon devices. But this is where I will stop for today. In the next video, we will continue exploring these fascinating devices.